Okay, reading number 3 in comparative biomechanics is one of my favorite papers, and I feel like I say that about pretty much every paper in this class, but this one's really one of my favorite papers. A 2009 narrative by Alan Walker titled The Strength of Great Apes and the Speed of Humans. Long story short on this one is that humans are very genetically similar to chimpanzees, another member of the group of species here called the Great Apes, which includes humans and chimpanzees and some other species of monkeys. We are very genetically similar humans versus chimpanzees. We're relatively similar in size and overall stature and mass. If anything, they're a little smaller than us on average, but they are enormously strong. Chimpanzees are enormously strong compared to a human. This study here suggests that they're like 4 times stronger than your average human. There's other studies that are a little bit more conservative there. This is probably the most extreme estimate of how much stronger a chimpanzee is, which is kind of why I like it. There's other estimates that say, well, maybe they're only about 50% stronger than us. But regardless of how you parse it out and what evidence you look at, chimpanzees indisputably are stronger than humans, and especially pound for pound are stronger than humans. And so why is that? That's really what this paper is getting into and trying to explain why chimpanzees appear to be so strong compared to humans. Let's revisit this notion here of great apes before we get into the guts of the paper here. Who are the great apes? I am a great ape. You guys are great apes. Humans are a member of this group of species called great apes here. I had a hard time finding a picture that has all 4 of the species all at once. This was the only one I could find. It's on Wikipedia here. At the top is humans, and these at least look like human children to me. And then there's also chimpanzees. There's a smaller species of monkey called bonobo, which is kind of like a mini chimpanzee, which is also included in here. But chimpanzees are kind of the umbrella term used there. So humans, chimpanzees, gorillas, who are much bigger than humans, and orangutans, who are also roughly similar in size to a human. So a gorilla is, of course, enormously strong compared to any human. Your typical like adult, full-grown male silverback gorilla can be well over 6 feet tall and can have like an 8 or 9 foot wingspan and is up to like 500 pounds of just sheer muscle. They're just extremely inhumanly strong animals because they are inhuman. They're not a human. They're a gorilla, and they're much bigger than a human, and just the sheer amount of muscle they have just vastly exceeds what any human would be able to carry. But chimpanzees are pretty similar to humans in size. Like a full-grown adult chimpanzee is typically somewhere between like 3.5 to maybe like 5 feet tall. Would be a very tall chimpanzee would be 5 feet tall, and they might weigh like up to like 150 pounds or so. Would typically be a pretty big adult chimpanzee, and so they're actually a little bit smaller on average than your typical human. Nonetheless, they are extremely strong in terms of how much force they can apply to external objects compared to how much force a human can apply to that same object. The Walker paper here presents some really interesting evidence on just how much stronger your typical chimpanzee is compared to a typical human. He reviews some older papers here from the 1920s by Bauman, where he tested the strength of what he called several fit young football players. He doesn't say if they were men or women, but I think only men were playing football in the 1920s, so these were presumably all men. They tested them on what he called a calibrated metal hoop dynamometer. Walker doesn't describe this device any further in this reading, and I've actually also tracked down these 2 1920s readings, and they don't really describe the device in any extensive detail and don't have a photo of it or anything. From the best of what I can determine, let me pull up my video here. The best that I can determine is that this calibrated metal hoop dynamometer is like a ring-like shape, just like a ring-shaped piece of metal. And if you imagine pulling on that ring and deforming it and bending it, if you know its dimensions and you know what it's made of, and from that know its material properties, then you can compute based on how much it deforms, how much force you had to apply to that material of that shape to get it to bend and deform by that much. I'm thinking is at least to my understanding of the description of the device in the older papers is roughly how it works. They then took that ring and chained it rigidly to like a concrete wall, and then on the other side of the ring fastened a rope and then the participants, either the human football players or the two chimpanzees in the study, would come and pull on the rope, and it would measure how much force they were applying in the pull on the rope. Again, I can't find a picture or a great description of the thing, but they describe it as a test of like arm and leg strength. And I think what's going on is, let's suppose like my power cable here for my laptop is the rope that's attached to the dynamometer there. I think you would like grab on it, and it would be kind of like tug of war. Like you would just pull on that rope with as much force as you could. Just pull on it as hard as you could. So they describe it in the Bauman papers as a test of leg strength and back strength. And so if you want to read the poundages here in terms of the strength in the Walker paper, in terms of what is it analogous to that we understand better, that we're more familiar with, I think it's probably sort of conceptually similar to like a deadlift exercise. So like these poundages here would be just a very crude approximation of what like a 1 rep max deadlift would be like for these people or for these animals. So how strong were they exactly? In the Bauman study, they had data on two chimpanzees, a female named Suzette, who is this cute little animal up here. Suzette was a retired circus chimpanzee. Suzette, along with being fairly strong, as you'll see, could also ride a bicycle, and so the circus was interested in her not for her strength, but for her bicycle riding ability. She got kind of ornery and fussy for a while when she was in the circus, so they retired her here to this university, and she was then a participant in Bauman's study here. So that's the female chimpanzee that they mention in the Walker paper. They also mention a male chimpanzee who is this fella down here, Boma. Boma was much friendlier and more mild-mannered than Suzette, but he was quite a bit bigger and stronger. I don't know if this is still the record. The Bauman paper is almost 100 years old here, but Boma at the time was the largest chimpanzee in captivity. He weighed about 165 pounds, which is quite big and quite heavy for an adult full-grown chimpanzee. And he wasn't like obese. He wasn't fat. A lot of great apes, when they're in captivity in zoos, unfortunately, will eat too much and will not get the physical activity that they need, and don't have the don't have the stresses for survival that a lot of chimpanzees in the wild might have, and can get kind of overweight because of that. But Boma here was not fat. He was in good shape and good fitness for a chimpanzee. He was just large and strong. So how strong were these fellas? The strongest student, and then these are, at the time, at least in the 1920s, fairly fit, fairly healthy young men playing college sports. And again, these poundages here, I think, are probably roughly analogous to like a deadlift exercise. The strongest human that they had in the study did a one-handed pull of 210 pounds. So imagine doing a one-handed deadlift with over 200 pounds. It's pretty darn strong. And then a two-handed pull of 491 pounds, so almost a 500-pound deadlift. That's pretty darn strong for anybody. How'd the chimpanzees do? The male they couldn't get the male to do a two-handed pull. He only wanted to do one-handed pulls. They note here that he had the animals, then in quotes, when they felt like it. You can't really order chimpanzees to pull as hard as they can at a specific time, or have any assurance that they're really pulling as hard as you can. So these are just the strongest pulls that the chimpanzees happened to do when they felt like pulling on the thing. The male did a one-handed pull of 847 pounds compared to 210 pounds for the strongest human, and the female did a two-handed pull of 1,260 pounds compared to 491 pounds for the strongest human. So even if you ignore the fact that the chimpanzees here are lighter and smaller in size than the humans, were tremendously strong compared to these humans. They were roughly 4 times the strength of the strongest human that participated in this study. These Bauman studies, again, are on the upper end of what has been reported for how much stronger chimpanzees are than humans. It's I think as far as I know, it's the one with the most extreme difference there in the strength levels. There's other studies that are a little bit more conservative that suggest maybe the chimpanzees are only like 50% stronger, 75, 100%, not 400% stronger. But regardless of how you splice it out, every study that I know of on chimpanzee strength, no matter how you define strength, no matter how you measure strength, suggests they're about at least 50 to several multiples stronger than your typical human, or in a qualitative sense are definitively stronger than a typical human. So, why is that? What is the source of that strength, and what can this teach us about human strength in terms of what might make a human strong? Bauman goes through several theories here, several ideas on why he thinks or why the great apes might be so strong, or why chimpanzees specifically might be so strong compared to humans. And these ideas are summarized here in these bullet points here. He doesn't really talk too much about this one here, this top one here that I put, sheer amount of lean muscle. That was one that I added there. But the possible sources of chimpanzee super strength could be one of, or some combination, I think, of these four things. They could just simply have a much greater amount of sheer muscle on their frame. Like if you're 150 pounds, but 100 pounds of that is lean muscle versus 50 pounds of that is lean muscle. That will, of course, make a huge difference in strength. They could have long muscle moment arms, which we talked about a little bit earlier in class. They could have greater specific tension of their muscles, which we haven't talked too much about. Or they could also have a greater capacity for truly fully activating their muscles, which we talked about a lecture or two ago. So let's visit each one of these in isolation here and see if we can learn something about what they are and how they might contribute to this observed seemingly superhuman strength in chimpanzees. Do chimpanzees have a large amount of lean muscle? I imagine there's anatomical studies on that. I don't think it's been observed that they necessarily have an extremely impressive amount of muscle on their bodies compared to humans, so this may not be necessarily a huge source of their sheer strength. It certainly looks to me like they have a lot of muscle on their bodies compared to certainly an average human, and maybe not so much compared to like a human athlete, but certainly a great deal more than your average human. Just as an example there, here is a picture of a chimpanzee who had a rare genetic condition where he had very little, if any, body hair on him. So this wasn't like a cruel experiment here. They didn't shave the chimp or anything like that. This chimp had a genetic condition where he didn't have much hair on his body. And look at the muscle on this guy. He is jacked. He has got some serious muscle going on there on his arms and on his back. And you can see even on his legs here, which are typically kind of short and stumpy for chimpanzees. He's got a lot of muscle there on his thighs. So it looks to me like a great deal of muscle on this little 100-and-some-pound animal here. And keep in mind, this is somebody who doesn't have any weights, doesn't do any strength training. Who knows what this guy's doing? He's just out in the woods living his chimpanzee life. So, and this is just kind of what he naturally looks like going through that life. If we saw a human that had arms like this, you'd be like, man, that guy's jacked. He must, hit the gym quite a bit. This is just what a typical chimpanzee here looks like, without any dedicated, specific training to looking like that or to building that muscle. So I think this is even though maybe there's not a great deal of evidence that chimpanzees have an unusually large amount of lean muscle, it certainly appears to me like they have more sheer functional muscle pound for pound on their frame than your average human does. Okay, that's the one that Walker doesn't talk about so much. These other three ones here is what he gives some attention to, and the one he eventually settles on, and the one that he thinks is the main reason, and the one that I also think is one of the main reasons, is this last one here: greater capacity for truly fully activating their muscles. That humans might have some, possibly due to lifestyle factors or safety factors, might have some inhibitions there in terms of truly fully activating our muscles that your typical like wild animal like a chimpanzee does not have. These other two factors here that he revisits or that he suggests are possibly not so strong explanations, but could also be factors onto why chimpanzees are pretty strong. So let's revisit that here. Longer muscle moment arms. What is that getting at exactly? And let's go back to our muscular chimpanzee here. This would be the idea that the chimpanzee either has unusually thick joints, which doesn't really look to be the case to me, or they have muscles that attach relatively high up on their body segments such that they have long moment arms. And that kind of looks like it might be the case here to me. Like I'm looking at what looks like a forearm muscle here for the chimpanzee, and it looks like it attaches up pretty high up here on the humerus of this chimpanzee's arm, much higher up than that analogous muscle would attach on a human. And this could possibly give you a relatively long moment arm for that muscle and give you some elbow flexion strength and some wrist strength that a human would not have, even if they had that same muscle in that body with different attachment points. Let's revisit this idea here that we've talked about in terms of moment arms and strength, because we talked about this before, but it's been a while, so let's just review that. So let's suppose that my water bottle here is not a water bottle. Let's suppose it's a dumbbell, and I want to lift that dumbbell. I want to curl it with my biceps muscle here against gravity, and I want to do this with the heaviest possible dumbbell. To do that, to perform that lift, I'm flexing my elbow joint here. And to do that, I need a flexion moment at my elbow. Okay? So it's most directly the flexion moment at the elbow, not the force in the biceps muscle that is lifting the weight. Okay, it's kind of a chicken egg thing because, like, yeah, there's the flexion moment at the elbow, but where does it come from? Well, it comes from the force in the biceps muscle, so they're kind of related here. But at the closest level of what's causing the motion that lifts that weight, it's the torque at the joint. That's the more direct cause than the force in the muscle. The force in the muscle causes the torque, but it's the torque that causes the motion and is kind of powering the lift. So how do I lift the heaviest dumbbell possible here? Well, I would want a really big moment at that joint, a really big flexion moment at my elbow joint. And where do I get that moment from? Well, I would want a really big force here in my biceps, and to then express a really big force there on my biceps tendon, and then to make that force become the biggest flexion moment possible, I would want to multiply that force by the longest possible moment arm, the greatest possible distance from that tendon to the center of the joint here that's rotating and moving that weight. Okay? So it's most directly in terms of like applying forces like with our body, like with our hands to an object. Lost my video here, sorry. Let's try that again. Sorry, guys. There we go. So it's most directly, if I want to talk about like the forces that I produce with my body in contact with an object to move that object against gravity, that's most directly caused by the torques that I produce at my joints that move those joints and press my hands into that object and apply forces to that object. Okay? Those moments then, of course, come from the forces in my muscle, but what transforms those forces into the torques that rotate the joint and move the object is that force combined with my musculoskeletal geometry, namely the moment arms, or the distance from my tendon forces to the centers of the joints that those forces are causing moments or causing torques at. So to produce the greatest amount of strength in terms of our classic definition of strength, like lifting or moving a heavy weight, you would want the biggest possible muscle force times the biggest possible moment arm. And that'll typically be accomplished by having a physically large joint that muscle wraps around. So if you look at, say, the ankles of sprinters, they're sometimes not the biggest, thickest ankles in the world. You might think that's weird. Doesn't a sprinter need strong ankles? For sure, a sprinter needs strong ankle muscles, but they don't necessarily have to produce a huge amount of torque at the ankle joint. They have to produce large forces with their muscles and lots of power with their muscles, but they don't necessarily need huge torques at the ankle joint in terms of like the largest possible isometric torque you could produce. Sprinting is not isometric. It's a dynamic task. It's a fast task. It's a power task. And there we're more concerned about muscular power and the rate of muscular force production, not so much about just producing the largest isometric torques possible. If I'm like a power lifter, for example, which actually isn't a very well-named sport. I think it should be called strength lifting or torque lifting or something like that. If I'm a power lifter, then I'm moving a really heavy weight fairly slowly, right? Like it's not like they try to move it slowly, but since it's so big and so heavy, they're typically in practice moving it fairly slowly. So the whole notion of the speed of the movement and the power of the movement doesn't really come into play as much as it does in something more fast and dynamic like sprinting. And so there in powerlifting, I'm more concerned with producing the biggest torques at my joints as possible. And there I'm going to want a big muscle force and also a big moment arm, which is going to best be accomplished by having a big joint that muscle wraps around. Okay, so that's why when you look at like really good, successful power lifters, they have big muscles, but they also have big joints, big, thick, wide joints, because that gives them a big muscle force multiplied by a big moment arm to get a big moment at the joint to complete that very heavy, relatively slow lift. So, differences in musculoskeletal architecture, possibly giving you longer moment arms at the muscles. If you look at the chimpanzee's muscular structure here, his arm doesn't look drastically different from a human arm, but you could possibly have some small differences in moment arms there that could make a relatively large difference in how much torque that animal can produce at its joints. The other factor that they suggest here that I think is possibly the weakest factor for why chimpanzees are so strong, despite what one of the conclusions on one of the next papers we'll read, is that they have greater specific tension of the muscles. Now, I don't think we've defined that term. We might have covered this a little while ago in class. I can't remember for sure. So let's revisit that again. Our simple model here for how much force a muscle can produce is F naught times alpha times FL times FV. And what were these things exactly? F naught is my max isometric force. This is how much force my muscle produces when it is maximally activated by the nervous system at its optimal length and at a velocity of 0. Okay, so when it's at whatever length produces the most force and not shortening or lengthening, it's just staying at an isometric constant length and maximally activated, then that muscle will produce its max isometric force. Now, what is the max isometric force exactly? This is a function of two things, the size of the muscle and the specific tension of the muscle. Size here is represented by PCSA, or the physiological cross-sectional area. This is the total cross-sectional area of fibers inside the muscle. The more fibers you have inside the muscle, the more force it's going to be able to produce. You take that physiological cross-sectional area times this sigma naught symbol over here, which is the specific tension of muscle. This is called the specific tension, like I've been calling it here. It's technically the force per unit cross-sectional area. You might also see it sometimes called the intrinsic strength of muscle, or the pound for pound strength of muscle. This you can think of as the strength of the muscle normalized to muscle size. So kind of scaling muscle strength by the size of the muscle. How strong is muscle on like a per unit area or per unit size of contractile tissue inside the muscle. This sigma naught, or specific tension, is in theory the same for all muscles, and not only for all muscles within like an animal, but for all muscles across animals. At least that's the idea behind it. That strength here in muscles in terms of max isometric force scales pretty closely with the size of the muscle in terms of its cross-sectional area. And the constant of proportionality here, if you took strength and divided it by size, that ratio there would in theory be constant between muscles and between animals, and would give you this ratio here, specific tension. In practice, if you look at studies on actually computing specific tension and comparing it between different muscles or between different animals, you don't typically see it being literally constant. You actually see a pretty wide range for it. Some say it differs by like an order of magnitude between different studies. It's a notoriously difficult variable to measure and to determine with any great deal of confidence and accuracy. So I think some of the spread in values that you see for it is less about this theory here, this model here being wrong, and more about this just being a very difficult parameter to actually measure with a good deal of confidence and accuracy. There have been studies comparing the specific tension of muscle in chimpanzees versus humans, and comparing them between muscles that are at least conceptually similar in terms of their role in moving certain parts of the body between humans and chimpanzees. The one that I'm aware of showed that chimps are up to like 30% greater specific tension than humans. And so it could be a factor that explains some of their greater strength. Their muscles are just intrinsically stronger for some reason. But it doesn't look like it's something that explains all of their strength. That's certainly being 30% greater specific tension would, for a pound for a given muscle here, would make you a 30% stronger max isometric force. but that doesn't explain the 2 to 4 fold greater strengths that you sometimes see in like pulling tasks, whole body pulling tasks, that like in the Bauman paper in terms of strength of a chimpanzee versus a human. So the most likely source here, I think, of strength for chimpanzees, and the one that the Walker paper suggests as the most likely source, is related to this activation level here. Okay? Alpha there, the activation level, that is the fraction of open cross bridges or open cross bridge binding sites on actin. We haven't talked too much about how muscle produces force at the microscopic level. That's something I cover in my other undergrad biomechanics class that a lot of you took before this one, but I haven't talked about it too much in this class. Muscle at a microscopic level consists of these overlapping bands of like thick and thin filaments. The thick filaments are called myosin and have these little like bulb-like heads on them. And the thin filaments, in terms of the set of overlapping filaments here, is called actin, and they have these little binding sites on them. When your brain activates your muscles, it floods the muscle fibers with some calcium ions. There's a whole bunch of like neurochemistry that I'm leaving out here, but those calcium ions flood into the muscle and they go into those thin actin filaments and they open up those binding sites. When the muscle's at rest, it has some things sitting on top of them that block them. They get opened up, and then those heads on the thick filaments on the myosin can grab onto a binding site and basically pull on it. So the way that your muscle produces force at the microscopic level is actually kind of like a tug of war. If you think of like a rope here being the actin filament and my hands here being the myosin filament, it's kind of like to produce force. I'm grabbing onto it and pulling, and then grabbing and pulling, and then grabbing and pulling, and repeatedly grabbing and pulling on that filament in a cyclical fashion to generate tension and generate force. And you have billions and billions of these tiny little microscopic myosin heads all doing this at the same time and generating little piconewtons of force that all adds up to like hundreds or thousands of newtons at the level of the muscle fibers and the tendons. So that's where muscle force comes from at the microscopic level. Each time you have that cross bridge of myosin grabbing onto actin and pulling on it, and then detaching and recocking and getting ready to pull on it and grab it again, that consumes one molecule of ATP, or one molecule of food energy. And so this is where, at least for a lot of types of muscle contractions, is where both the like mechanics side of muscle comes from, and also the metabolic or energetic side of muscle comes from. So it's a nice simple model relating the mechanics and the energetics of muscle. So the activation level here in our simple model here of muscle force is the fraction of those binding sites on actin that are open and unblocked and available for a myosin head to grab onto it and pull it and generate a little piconewton of muscle force. In terms of how many of them are open at any one time, and again, I'm leaving out a lot of details here, the amount of them that are open and available increases with the general intensity of the commands from your nervous system, or the neural excitation level, or how intensely the brain is asking the body to use that muscle. That'll be a function of two parameters here primarily: your motor unit recruitment and your motor unit rate coding. The way that the brain kind of grades up and down muscle force is you have these motor axons that connect to groups or like batches of muscle fibers in a muscle. And so that kind of functional unit there, the motor neuron and the muscle fibers that it innervates, that's a motor unit. Okay. So to increase muscle force, you can either recruit more motor units, like recruit more total muscle fibers to produce force, or you can increase rate coding, which is how frequently you are asking those motor units to produce muscle force. Okay. So both of these things will generally increase with the intensity of how much our brain wants us to use this muscle, and that will increase our activation level, and from that potentially increase muscle force. So for a variety of reasons, perhaps due to lack of practice, perhaps due to lack of need to actually do it, or maybe due to safety in terms of producing forces that are so big that we would tear something or damage something in our bodies. There's some arguments to be made that Walker makes, some of them here in the paper, that perhaps humans can't actually maximize our activation here. Perhaps we can't truly open up and produce force at all of the binding sites on our muscles. Whereas a wild animal who might need to do that every day for just basic survival is perhaps much more capable of doing that, or has much less what we might think of as a neural inhibition to truly recruit all of their motor units and truly fire them at all of their maximum rate coding rates. So a number of reasons here why chimpanzees appear to be stronger than humans. To me, I think the two best candidates are number 1 here and number 4 here. A large amount of lean muscle pound for pound on these wild animals compared to a human of similar size, and a greater capacity for full activation. This last one here, I think, has some important implications for human strength performance, in that strength, in terms of like powerlifting, Olympic weightlifting, that sort of thing, isn't just about muscle, isn't just about having a lot of muscle. It's also a very prominent neural component in those activities. And anybody who's into like powerlifting and lifting for 1 rep maxes and things like that, this will be no news to anybody that's actually in those sports. There is a huge neural component to strength that I think we sometimes underappreciate in kinesiology. It's not just about having a lot of muscle tissue. It's about being able to activate that tissue and make use of that tissue, both in terms of like the brain activating it and recruiting it, and also your technique, being able to direct the force from your muscles to outside the body to effectively moving the weight that you're trying to move. Okay, that is it for today. We will wrap up next time with 2 papers that kind of extend this idea. One showing how the greater strength of chimpanzees helps them out in a task like jumping, and one showing where it does not seem to help them out in a task like throwing, which humans are kind of uniquely good at. And we will see you next time.